Hello everyone. Today we are going to have the 8th episode on alcohol, phenols and ether. What I am going to illustrate today is about the preparation of ether. It would be easy to learn and mug up when we classify the preparation on the two heads. So students, please let us see the board as we go forward in making the preparation of ether. Here we go. In the preparations of ether, the first point what it comes to our mind is from alcohols. It is much easier to go from alcohol, and we know that concentrated sulfuric acid and anhydrous aluminum oxide or alumina, they are very good dehydrating agents. They absorb the chemically formed water present within this compound. So let us see how they snatch out the water molecule from this very compound. And at the same time, the change in the temperature would be affecting it. So let us see how we do. This is C2H5OH, 2 moles. It will join it as C2H5 and then one more C2H5, and it is having an oxygen bonded to it, and it forms diethyl ether or ethoxyethane, and together what it comes is the formation of water. So a water molecule come into existence. So if I do like this, C2H5OH and C2H5OH in a U-turn, C2H5OH, what it happens is a molecule of water escapes out when you add Al2O3 or concentrated H2SO4. Only the temperature difference is very important. What it happens is this C2H5 links up with the oxygen present with the other alkyl group to form the ether, and together with it we get here the water molecule. This is what happening. Now this similarly with concentrated sulfuric acid also, it would be similar, saying C2H5O, C2H5 with a liberation of a molecule. So when we take alcohol and allow concentrated sulfuric acid to pass at a temperature of 413 Kelvin. Now student, be careful while you go with this type of equations. The temperature is very important. Here 413 Kelvin, here 512 Kelvin. Now you see here they form the diethyl ether. Now see, if we change the temperature from C2H5OH and we give here concentrated sulfuric acid at a temperature of 443 Kelvin. So 443 Kelvin, if we give this temperature, what is the effect? The effect is very simple. They take out the water and it forms here ethene, CH2, double bond CH2 with a loss of the water molecule. So student, here you can see the carbon, if we see the mechanism here, CH, H, and OH. What happens when you are giving a temperature of 443 Kelvin with concentrated sulfuric acid? So this molecule of water is liberated. Here what was happening, 2 moles of the alcohol was used, and here there will be 1 mole of the alcohol being taken, and there will be a loss of water to form the corresponding alkene. So you can see here the hydrogen forming with the bond with carbon, and then carbon making a double bond with the other carbon making an alkene. So in this preparation there is a limitations, and the limitation is that we have to give sufficient amount of alcohol, because together you cannot sometimes control the temperature, and the temperature sometimes exceeds, and if it exceeds it forms an alkene. To limit the amount of the alkene, we have to give a huge quantity of alcohol. This is one limitation on the preparation from alcohol from aluminum oxide or alumina and concentrated sulfuric acid. Now there is another more limitations that we are going to see, that is this this is applicable for the primary alcohols. Had it been for the secondary and the tertiary, let us see. It is not going to form ether. Can you just imagine that this is applicable only for the primary alcohols. For the secondary and the tertiary alcohol, let me go with this compound saying this is CH3 and CH3 and H. So now when you are taking concentrated sulfuric acid to a temperature of 413 Kelvin. So when you are giving this temperature, what it is happening, let us see. It is forming, so this H and the OH, they will be uniting together to form the water. So there will be a loss of the water molecule. So what is remaining is the CH3 here and then C, and this double bond, like this H and this H, it goes off H, and here double bond CH2. So you can see here it is forming a compound like CH3, CH, double bond CH2. You are getting here one propene, PROPENE. You are not going to get ether at all. So in the preparation from the secondary alcohol with concentrated sulfuric acid or aluminium at 525 Kelvin, you are not going to get the major product is an alkene. To some extent there can be the formation of ether, but the major product is the production of alkene. So an unsaturated hydrocarbon comes. If we go with the tertiary alcohol, say this is tertiary alcohol, this is tertiary alcohol. With this tertiary alcohol, when you are allowing concentrated sulfuric acid to pass through it for a temperature of 413 Kelvin, what it happens? One hydrogen from here, another this hydroxide, they unite together to form water. So let us remove this water. H2O is being removed, and what you have here is CH3, single bond CH3, and then double bond CH2, and this H and this OH, it elapses off, it runs off, and you get here a compound. What is the name of this compound? Can you tell me here, students? CH3, C double bond CH2, and here CH3. You will be having 2-methyl, METHYL, 2-methyl, prop 1 in, prop 1 in. So from the tertiary alcohol, from 3-degree alcohol, you are going to get 2-methyl prop 1 in. With 2-degree alcohol or secondary alcohol, you are going to get 1 propene. So you are not having your safe compound, that is ether. So temperature is very important here, that if you give a temperature above 413 and it is going to become alkene, so the amount of alcohol to be given as a raw material should be in a huge quantity. And another thing what we have learned is it is applicable only for the primary alcohols. Had it been for the secondary and the tertiary alcohol, our idea or our goal or destination of reaching the ether is becoming impossible. So in the second preparation or the preparation of ether, in a different way we can see Williamson synthesis. What is that? Let us understand. Sodium alkoxide, when we are going to react with alkyl halides, it gives you ether and solid. This is what Williamson synthesis speaks about, that sodium alkoxide. So if it happens, you take your sodium alkoxide or sodium phenoxide. This is sodium phenoxide, this is sodium alkoxide or ethoxide. So when you are treating it with alkyl halide, you will see there will be a nucleophilic substitution reaction. And in this nucleophilic substitution reaction, what happens? This Na reacts with the Br, forming NaBr, and the sodium ethoxide joins with the ethane, or if it is methane here, you can add it here, methane. Similarly, if it is sodium phenoxide, you are reacting with C2H5Br, you are going to get here, what you are going to get, student? You are going to get here C2H5O, C6H5. What is the name of this compound? It is, come on, we call this as, can we call it as phenoxide ethane or ethyl phenoxide? So we usually say as ethyl phenoxide. Why? Because we have already stated before that the number of the carbon, if it is less, it will be adjoining the oxygen atom towards it. So we usually produce the name with the least number of carbon. So it is ethyl oxide and then phenol. So the phenoxide. So here what we say it as the ethyl. So we have here this oxygen attached to the ethane. So we call this as ethoxybenzene, Benzene. And here what we call it as ethoxy, ethoxy, ethoxyethane. So you get here, students, the word ethoxy comes with the least number of the carbon containing the hydrogen. So here ethoxybenzene. So here what we have seen in Williamson synthesis is that when you are going to react with the sodium alkoxide and alkyl halide, you are going to get an ether. So what is the formula? Let us see. Now this Williamson synthesis, if we see the mechanism, if we want to see the mechanism, say here we have a benzene, or we can call this as a phenol. When you are adding sodium hydroxide, then what comes? It joins up with the liberation of ONA, H and OH forms water. So water will be lost and sodium phenoxide is going to form. Now when you are going to put in the water, it breaks up into the phenoxide part O minus and Na plus. So this is the mechanism. So this the bond here, they take this oxygen takes the electron, sodium gets positive charge. Now in the second line what you will see is that in the second line we will take this phenoxide ion, we will be taking this phenoxide ion, and when we are going to react with like C2H5Br, this also becomes this Br and C2H5. You can see this electron get transferred, this is negative and this positive. So this positive charge will be taking the oxygen and it forms here, the benzene is formed here, oxygen and C2H5, while this Br and this Na, this Br minus and this Na, in the third line, you can see the third state, you can see this Na plus and Br minus, they join together to form NaBr. So this is the mechanism, student, that the phenoxide ion is being formed together with the liberation of sodium ion, and the phenoxide ion reacts with the ethyl bromide or alkyl bromide or alkyl halides except fluorine to form this the ethane with the oxygen and the benzene. So we call this as ethoxybenzene. So students, you have already learned the preparation of ethers right from alcohol and number 2 by Williamson synthesis reaction. Now there are some limitations in Williamson's also. So let us see vividly what are the limitations that we see in Williamson synthesis. The first point to go is aryl halides and sodium alkoxide cannot be used to prepare phenoxide ethers. This is very important, that we cannot make phenoxide ethers by this process. Why? Because aryl halides, and sodium alkoxide cannot be used. What is the reason? Why not aryl halides? The answer is very simple. Since aryl halides are much less reactive than alkyl halides, so we cannot use aryl halides because it is a very less reactive and it cannot undergo nucleophilic substitution reaction. This is the first point that you have to know. I repeat, aryl halides are less reactive than the alkyl halides. like C6H5Cl is very less reactive than C2H5Cl or C2H5Br. So aryl halides are less reactive than alkyl halides because they will not undergo the nucleophilic substitution reaction, and our determination of reaching to ether will be unfulfilled. The second point that I would like to show you here is, in order to prepare unsymmetrical ethers, alkyl halides should be primary. Remember, it should be a primary one, 1 degree alkyl halides. Since secondary and tertiary alkyl halides yields alkenes. So instead of giving you the ethers, they are going to give you alkenes instead. I have got some examples to illustrate it. Like I have given here 1 degree alkyl halide. This is 1 degree alkyl halide. I am giving you a tertiary sodium alkoxide. So here what the reaction it will be, let us see. If I remove this line to get the more and more workstation, I will show you in the limitations of the second part of Williamson synthesis. What is the reaction you will be having is that this portion, this NaBr will be removed. NaBr will be removed, and here you have CH3CH as usual, and then it joins oxygen and then carbon with CH3, so CH3. So here tertiary is possible because here you have the primary. Primary alkyl halides should be used. You cannot use secondary and tertiary. I have shown you at second example with the tertiary. In the tertiary what happens, you can see this sodium and bromine runs off in the form of sodium bromide. Sodium and bromine reacts together to form sodium bromide. Now, this oxygen takes a hydrogen from the alkyl path. So it becomes here CH2. So it becomes here CH2. One hydrogen removes, and here this H with O and CH3, it forms CH3OH. It forms methanol. So here you are to get is alkene. So you are going to get here alkene. So student, what you can see here is you cannot take tertiary alkyl halides. With tertiary alkyl halides, it is going to form alkenes. So it is applicable only with primary or 1 degree alkyl halides. It cannot be used for secondary or tertiary alkyl halides. And the third point, and this is the third point, what it says, this method cannot be used for the preparation of diaryl ethers. So this is the diaryl ethers. With Williamson synthesis reaction, you cannot undergo the preparation of diaryl ethers. This method cannot be used for the preparation of diaryl ethers, since aryl halides do not undergo nucleophilic substitution reaction. This is very simple, what I have stated you before. This aryl ethers, diaryl ethers, we cannot make it because aryl halides are very weak, reactive. They are very weak in their reactivities, and they do not undergo nucleophilic substitution reaction. So these are the 3 points that you have to learn through while you do the preparations of ether. So student, today you have learned about the preparations and the limitations. You learn it nicely, and in the upcoming video we will be going with the properties, particularly the physical and the chemical properties of ethers. Till then, goodbye.